So first, to start with, a little bit about me. I've been a C++ software developer at Jump Trading since 2014, so about 7.5 years now. Jump is a global trading firm committed to world-class research and development. Our focus is to be the best trading firm in the world across all asset classes and all time horizons, not just HFT. We design, develop, and deploy technologies that are the leading edges of the field. We fund startups across universities, and we partner with leading global research organizations and universities to solve problems. And we're always looking to add talented engineers to a variety of teams. And we have a great mix of experience across different industries. So if you're interested at all, feel free to reach out and check out our LinkedIn page for open roles and reach out if you have any questions. As Fred mentioned, I've been an active member of the C++ Standards Committee since about 2016. I've been kind of responsible for a bunch of stuff that's in C++ 20, including Spaceship, at least the equality parts that may or may not have broken your code. I'm sorry. Pack expansion in Lambda and capture, conditionally explicit and conditionally trivial special member functions. And as well, recently added for C++ 13, I was one of the authors of the Deducing This paper, which I'm pretty excited about, as well as if const-eval. And also throughout all this time, I've been responsible for a whole bunch of different ranges papers, hence my interest in this topic at hand. I'd also like to introduce Hannah, who is my life mascot and who is my avatar across all of social media. And she recently turned 15 and is just as spry as ever. I have a blog that you can read, although I post pretty rarely, maybe every other month or less frequently. You can find me on Twitter, and you can find me unreasonably often on StackOverflow, just under the name Barry. Outside of the C++ world, I'm a very avid swimming fan, to the point that I actually write data articles for SwimSwam, which is the premier swimming news organization. And I also do data analysis and research for the DC Trident, which is a professional swim team in the International Swimming League, and features Tokyo Olympic gold medalists Zach Apple and Anna Hopkin. All right, so let's get into the topic. Let's say we have some sequence of numbers, and that sequence could be contiguous. It could be contiguous but slightly disjoint, like a rope or a deck. It could have embedded nulls that we have to skip, like an open address hash table or colony. It could be a linked list. It could be a binary tree. It could be a linear chained hash table. It could be something like a generator that creates elements on demand for us that doesn't have a in-memory representation. Regardless of what kind of sequence we have, it's important that we have some kind of uniform access pattern. Because if we don't have a uniform access pattern, we can't really write algorithms that can work on different kinds of sequences. We'd have to write bespoke code for every case. And that's fairly tedious. And so we need to have some sort of basis on which to build our model. And when I was thinking about this, the way I approached naming these basis operations is that we need a read operation. We need some way of accessing what is the next element in the sequence. We need an advance operation, because it's not very interesting if all you get is the same element over and over again. And you need some kind of done operation. You need some way to know when the sequence has been exhausted, so you can move on and do something else. It's important to note that these aren't necessarily three distinct functions, and we'll see several different examples of models that implement these operations in very different ways. But to start with, this being a C++ conference, we should start with the C++ iterator pair model, which was introduced by Alex Stepanoff as part of the standard template library in the early 1990s, which was then included in the original standard library when C++ was first standardized in 1998. So as to kind of go over the iterator pair model pretty quickly, we have a pair of iterators. The first iterator points to the first element. The last iterator points one past the last element. And these two iterators denote a range from one to the other. And what you can do with these iterators is you can advance them. You can move forward. If the iterators are bidirectional, then you can decrement them to go backwards. You can even decrement the end iterator. It's important to note in the iterator model that both the front and the end iterator can be incremented or decremented. The model supports both. For random access, you can also jump around an arbitrary amount directly. So you can plus equals 2 rather than incrementing twice. And so the iterator operations map pretty cleanly onto the basis operations that I described. The read operation is iterator dereference. Advance is prefix increment. And done is a little bit more involved because an iterator itself doesn't have enough information to know when it reached the end. You need that second iterator. So you need to do it equal last to know when you're done. And so if we look at the basic structure for C++ range, in C++20, this changes a bit because no longer do we need begin and end to return the same type. Now end is allowed to return something called a sentinel, which all it has to do is compare equal to an iterator. It doesn't need to itself be an iterator. And so if we look at the structure, we see our read operation is again operator dereference. We have our advance operation, which we have to provide both prefix and postfix increment. And we have our done operation, which is the two different equality operators that we have here. As we iterate through our range, we will consume this iterator. It'll slowly move on to the end, and then we throw it out because it's a cheap thing that we don't have to worry about keeping around. But the range and the sentinel themselves are not consumed. These kind of stay around. Of course, as you're iterating, you could modify elements of the range, but the range itself is not consumed by this operation. And you saw, if you look at it, this is already kind of like a lot of code on the screen, and there will be a lot more code. Don't you worry. But we have 3 different types on here that we might have to deal with, and there's 9 different functions already on the screen. If we look at the basic C++ range structure, like how would we actually loop over our arbitrary sequence? You can see that the first things we have to do is we have to pull out the iterator and the sentinel using ranges begin and ranges end. And we first check to see if we're done. Then we read that element that we have, and then eventually we advance onto the next one, repeat until done returns true. Of course, we have a range-based for statement to do this for us, so we don't have to write all this code. But it's sometimes important to go beneath the abstraction layer and see what's really going on under the hood. One of the cool things that we have in C++20 with the adoption of the ranges library is this new ability we have to adapt ranges. And I'm going to go over the 2 most commonly used range adapters, which in C++ are transform and filter. So what transform does is it takes a range and a function and applies that function to every element in a range, producing a new range. And this is done lazily. We're not allocating memory. We're not doing all of this work up front. We're just producing new elements on demand. Now, C++ calls this transform, but basically every other language I'm aware of calls this map. So for the purposes of this talk, I'm going to take the majority vote and just refer to this adapter as mapping rather than transforming. So in order to implement a map view in C++, we of course need the underlying range that we're adapting, which is base here, and we need the function that we're going to invoke on every element, which is fun. And this being a range, we need to provide a begin that returns an iterator and an end that returns a sentinel. But this isn't quite complete. We also, in some cases, want end to also return an iterator. Ranges that actually return an iterator from end are called common ranges. And if the range that we're mapping is common, we want to preserve that property in our map as well. And this is really important because if the underlying range is bidirectional, that allows you to iterate backwards from the end. But you can only do that if end actually returns an iterator. And so there's nothing inherent about mapping that would prevent that from working. So if you can itenerate backwards, if you can reverse the underlying range, we will also want to support that operation as well. This still isn't complete because we also need to handle consideration. So in C++20, some ranges are not considerable and some are, and we need to handle these cases properly. And so in order to do that, we have now not just iterator and sentinel, but an iterator and sentinel that are templated on whether or not they're const iterator and const sentinel. So let's go over the iterator real quick. So of course, when we're adapting an iterator, we need the underlying iterator that we're adapting. This is the base range that we're transforming, and we need a pointer to the parent, and this is going to be our way that we access the function that we're invoking. This is the way that it's specified in the standard, although it's more performant if the function object is small to actually move it into the iterator itself for additional locality. We have a bunch of aliases that we need to provide that I'm not really going to go over for the purposes of this talk. But of course, we need a way to construct the iterator. We have the simple constructor that just takes the parent and the iterator that initializes the members. But we also have this other one because we're used to the fact that a const iterator can be constructible from iterator. You can imagine the extension of pointer that t const star is constructible from t star, but not the reverse. So we need to make sure both that we support that operation, but in the correct direction. So let's get into the meat of this iterator. And you see these are the important operations. These are the basis operations that, as I've laid them out. We have our read operation. So iterator dereference is implemented in terms of dereference of the underlying iterator. And what we have to do is apply our function. We have to invoke parents fun on the element that we get out from reading the underlying iterator. Now, advancing doesn't have anything special attached to it. We simply advance the underlying iterator. And same with the done check. There isn't anything special about mapping for either of these operations. If we collapse this code a bit so that I can also fit the Sentinel on the screen, the Sentinel has this added complexity that const or non-const Sentinel needs to be comparable to const or non-const iterator if the underlying types support that. So the constraint here is fairly involved, but all we really have to do is defer to the underlying equals. So this isn't especially complicated either. And so what we can do is we can actually fit the entire map implementation on one screen. And obviously the code font is very small and I don't expect anyone to read that. But I'd like to point out that there's 5 types that we have to support here. I mean, you might quibble and say that we should really only count it as 3, but since 2 of them are templates and we really have to worry about both instantiations of each of those, I think counting to 5 is pretty fair. And there's a lot of functions here that we have to implement. Now, all of these functions are very simple. Actually, every single function here has its body consists entirely of return followed by an expression, which is about as simple as functions can get. But there's still a lot of them that you have to implement. And importantly, the only real salient aspect of map view is the invocation, right? What we want out of map view is invoking a function on every element. And that's what happens in this red box right here. And everything else outside of that box is kind of boilerplate that we have to write to satisfy the model. So let's talk about filter. Filter is interesting because it has this extra problem as compared to map, which is how do we make begin work? For map, the first element of the mapped range is just the first element of the underlying range with a function invoked on it. But for filter, that's not necessarily the case. The first element of the filtered view could be the first element of the underlying range. It could be the second, it could be the fifth. There could not even be an element that satisfies the predicate. So we need to make sure that we handle this case properly. And one of the important parts of the C++20 model is that begin has to be amortized constant time. And so we know that we have to do some kind of linear search in begin, but in order to meet that requirement, we have to cache the result. Right? So we hold on to an iterator that we cache, and when we call begin, if that iterator isn't initialized yet, then we do our find if. Otherwise, we just return it directly. As a result, filter cannot be considerable because we have to mutate its member cache as we go in order to support this requirement. Of course, as with map, we also want to be common where possible. So again, we have these 2 ends in addition to our 1 iterator begin. So if we look at our iterator, we again have the underlying iterator that we're adapting and a pointer to our parent that we need. We have our constructor to initialize our members, and we have our operations. In this case, read doesn't do anything special. Once we've found the element that satisfies the predicate, reading is just a matter of reading the underlying iterator. Advancing is more involved because not only do we have to advance the underlying iterator, but we also have to do the search. And this is why it's important to hold on to the parent, because not only do we need the predicate that we're checking for, we also need to know when to stop searching. Eventually, this has to terminate, and we don't want to run off the end. And as with map, the done operation is also nothing special. We simply defer to the underlying iterators equality. So if we collapse this all again, the sentinel here is simpler because we don't have this const or non-const sentinel issue. We just have a non-const one. So we don't need that complicated constraint, and we simply do equality. So again, if I collapse everything down so that it fits on a screen, despite having a very small font, you can see that here we actually do only have 3 types, but we have 13 functions. And as with map, the salient aspects of this adapter are pretty small. And in this case, they happen to be duplicated. We have this find if that shows up in 2 different places in the code. And personally, I think it's better to just write it twice than figuring out a way to avoid repeating that. But it's still kind of annoying in a way that there's all the stuff that we have to write, and it kind of hides the important aspects of the adapter. So we might think about, how can we do this differently? Like, what is a different approach to the iteration model? So let's talk about D. The D ranges model was introduced partially by an Andrei Alexandrescu talk in 2009 called "Iterators Must Go." I don't actually know if there's a good video of this talk, which is unfortunate because Andrei is such a great speaker, but the slides to it are at least fairly easy to find. Now, I don't expect people here necessarily to be familiar with D. I'm personally not super familiar with D as a language, but it's still interesting to go over what the range model looks like in D. In C++, we had a pair of iterators, but in D, we just have a single object, which is one range, which I'm illustrating here with this brace at the bottom. And the range encompasses all of its elements. Now, the operations that a range supports are pop front, which drops the leading element of the range. And just like in C++ iterators, where incrementing doesn't touch anything about the underlying sequence, it just changes which elements are in the range. Pop front doesn't do anything to that 483. It just changes which elements that this range refers to. If the range supports it, we can also pop back to drop the last element of the range. And notably, there's no unpop front and there's no unpop back. Ranges in D could only shrink. Now, this is a safe operation in the sense that a range knows when it's safe to shrink because it knows when it's empty. But we'll see situations where this becomes pretty interesting. And if a D range is random access, it also supports an operation called slice, which can drop arbitrary amounts of elements at either the front or the end. And you can just select whatever you want from the middle. These operations map super cleanly onto the basis operations that I've described. The D model is actually very similar to the C++ one in this sense. Now, in the D language, these aren't necessarily function calls, but for the purposes of this talk, I'm presenting all the models in C++ code, just for convenience. The basic do range structure just looks like this. In C++, we would have the same kind of aliases that we have in the C++ model because they're pretty useful. And we have front, which returns a reference. That's a read operation. Pop front, which advances, and empty, which is our single done check. Note that none of these operations are const. There's no such thing as a const iterable D range because it's the range itself that's consumed. And so there's no real benefit to making any of these const. We only have one type, it's just the range, and we just have these 3 functions. There's no additional stuff that we have to provide. To kind of help illustrate how this model works, we can easily construct a D range out of a C++ iterator pair, even if it's just an input iterator. And we can do that by having front dereference the iterator. That's what reading does. Pop front increments the iterator. There's our advance. And empty is our done check, and that checks first equals last. So these operations map pretty cleanly. A basic D loop looks very similar to the C++ loop. We're just basically calling differently named functions. First, we check if we're done, then we read the next element, and then we advance it. It's worth pointing out that here we're taking the range by value, whereas in C++ we took the range by reference. This is because D ranges are intended to be cheaply consumed, whereas in C++, that's not necessarily the case. So let's go over the same map and filter examples to really help drive in what this model actually looks like. So if we implement a map range in D, we again have, of course, the underlying range that we're mapping, and we have the function that we're invoking on every element that we need to construct. And we have to implement our basis operations. Similar to the dereference operator for C++, in D, front has to invoke basis front and invoke the function on it. And advance and done simply defer to the underlying ranges operations. And that's it, actually. And now we're done. We have just the one type, and we have the 4 functions, and we have a complete implementation of map in D. That's all there is to it. Filter in D, just like filter in C++, is a little bit more complicated because we again have this problem of how do we make sure that we get the first element correct. Actually, in D, it's a slightly bigger problem. In C++, we only had one entry point. We had to make sure that begin returned an iterator to the first element, or end if there is no first element. But in D, we have 3 different entry points. Like, we don't know if the user is going to call front or pop front or empty first. And so we need to make sure that all 3 of those functions do the right thing. So the way that the D standard library handles this case is it has this notion of priming. So there's an extra flag here called primed, and a function prime, which what it does is if we haven't primed the range yet, what we do is we first make sure that we pop off elements off the front until either the range is empty or the front element actually satisfies our predicate. And once we find the element, then we marked primed as true so that we don't have to do this again. Of course, we don't want to write raw loops for all these algorithms, and there is a name for this loop, and that name is findIf. Note that in C++, algorithms return iterators, while in D, they return ranges. So here, when I call findIf with a range, instead of just getting the single iterator that is the first element that satisfies the predicate, I get a range starting from that element all the way to the end. Okay, so now once I have priming, I can go ahead and implement all of my basis operations. And if I kind of rearrange the code this way, you can be it's a little bit more clear, and you can see that the first thing that every function does is call prime, which ensures that okay, now for sure we have a valid range. And once we call prime, then all we have to do for front is call the base front operation. Pop front calls the base pop front and does another search to find the next element, and empty calls the base empty. And so here, again, we only have the one type, and we only have 5 functions that we need to implement. So it's a much smaller, more concise implementation than we can do with the C++ model. Let's talk about C#. C# is a little bit different from C++ and D as far as what its iterator model looks like, but it's still pretty similar. So in the C# enumerator model, we only have 2 functions. We have current and we have move next, where move next actually satisfies both the advance and done operations. If we look at the same print all loop in C#, what we see is we actually start by calling move next. So enumerator, when it's constructed, instead of referring to the first element, it kind of points before the first element, similar to the way that the end iterator points past the last element. So the first thing we have to do is advance up to the first element if there is one. And if there is a next element, then we can read it and print it. So it's a slightly different approach to this model, but they're still pretty similar. And what all 3 of these language models have in common is that they have read as a distinct idempotent function. And so what I mean by that is whether that's iterator dereference in C++ or read or front in D or current in C#, this is an operation that you can call to get the current element, and then you can call it again, and it'll give you the same element again. That operation isn't necessarily free. As we saw in the map case, reading that element will invoke the function. So if you read it again, it will invoke the function again. This is why it's important in these languages that if you do mapping, that your function returns the same value every time for the same inputs. And this is really useful because if you need to kind of access that value multiple times, you have that, and it's easily available to you. But this has one very interesting downside, which is, let's take a look at this example. So what I have here is I have a vector of ints, and I'm mapping some operation onto it, and that operation just takes an int and returns an int. And I'm not going to tell you what it does. And then I have a filter because I only care about the even results afterwards. And once I build up this pipeline, I'm going to iterate through every element and print all of them. And my question to you is, how many times is some operation invoked? Now we know for sure that the answer is at least 6. Because if some operation, for instance, returns 0, such that every element would satisfy the filter, we know that we have to call it on every element to check to see if it satisfies the filter, because we might have to print all of them. But is it more than 6? It's kind of an interesting question, and it's one that people will run into pretty quickly once they start playing with C++ ranges. So if we look at kind of the salient operations to try to answer this question, I just have the maps read, filters read, and filters advance on the screen here. So when we're reading through the filter iterator, when we're in our loop printing every element, we need to read through the filter iterator, which reads through the map iterator, which has to invoke the function, right? And so this is how we produce that element that we're printing. But then when we go to advance the filter iterator to find the next element, that involves this loop where we're invoking the predicate on every element, which involves reading through the map iterator, which again involves invoking the function. So what this means is that elements that satisfy the predicate are transformed twice. This is sort of inherent to the way this model works. And this is something that I've seen lots of complaints about on Reddit or Twitter about the fact that this function is invoked multiple times. And I want to make it clear, and I want to point out that this is not unique to the C++ approach to ranges. If we look at the D model, for instance, we see this very similar kind of structure where reading through the filter iterator reads through the map iterator, which invokes the function, and then advancing the filter range in this case, advancing the filter range also has to read the map range, which also invokes the function. So we again have the same behavior where elements that satisfy the predicate are transformed twice. And C#, even though it only has 2 operations instead of 3, still has the same kind of shape where we're necessarily invoking the transform function twice. So this is kind of inherent in the model. Okay, this is the price we pay for having read and advance as distinct operations. So even given that, I've kind of shown that the D model is clearly simpler, right? A map was 18 functions in C++, but it's only 4 in D. Filter was 13 functions in C++, but it's only 5 in D. Obviously, the D model requires less code overall, and the D model predates C++ ranges. The Iterator model is older than D, but Andre gave his talk several years before Eric Niebler even started working on what eventually became Range v3, which eventually became C++ 20 ranges. And he was certainly familiar with this model at the time. So the question might be, why didn't we copy the D model since it obviously seems simpler? So let's look at our favorite algorithm, findIf, to try to answer this question. So let's say I want to find the first element that satisfies the predicate. So that's findIf. That is a pretty easy algorithm to implement in C++. It's a pretty easy algorithm to implement in D. And you can see that the loop structures for both algorithms are basically the same. These are very closely related. The only difference is that in C++, we return an iterator, which points to the element that satisfies the predicate. In D, we return the range starting from the first element that satisfies the predicate. And so this is fine. Now let's consider a slightly different problem. Now, I don't just want the element that satisfies the predicate. I want the range until the element that satisfies a predicate. Now, in C++, because any 2 iterators to a range themselves form a range, this is very easy to do. I call findIf. That gives me what will become the end of this range that I'm returning, and I return a new subrange that from first to it. And there we go. I'm done. Algorithms in C++ are very easy to compose like this, just as a result of this model. In D, okay, so we might start out doing the same thing. We call findIf, but now what? Now we're kind of stuck. because, okay, so I got the last half of the range, the one that starts the element that satisfies the predicate, but in D, I can't go backwards. There's no way to kind of say, give me the range from range to R. There's no way to flip it. That's not part of the model. So I can't really do it that way. However, as I've already demonstrated, it's easy to write range adapters in D. So I could start by just, okay, well, let me just write until range as an adapter, where front and pop front simply defer to the underlying range, and empty checks both either the underlying range is empty or I finally found an element that satisfies the predicate. So that's kind of our terminating condition. And so here is an implementation of until that returns an adapter. And this does the right thing. This does give us the same elements that we want, but the C++ algorithm is eager while the D one is lazy. So it's a little bit different. And we can even, this until range that I wrote is actually just a very useful thing in its own right. Typically, we actually invert the predicate and we call it take while instead of take until. But that's still a useful range adapter to produce. But we still want like an eager solution. So let's see if we can produce that. So rather than take while, we can create a take. So what take does is it produces up to n elements of the underlying range. So front defers to the underlying front. We're not doing anything with the elements themselves. Pop front both pops the underlying range and decrements our counter. And so that we're empty when either the counter reaches 0 or the underlying range is empty, because we don't actually know necessarily how many elements they are. So we may need to stop even before we've consumed n elements. And we can use this range to then produce an eager algorithm. So what we can do is count the number of elements that we need to take. So instead of having an iterator that into the first element that satisfies our predicate, we just have a counter. We have n. And then we can use n to return a take range. Now note that the first thing I'm doing in this algorithm is I'm copying range to hold onto it. This is because we're consuming range in that loop. D actually calls this operation save, but that has to do with the D language itself. And in C++, we would certainly use like the copy constructor to copy things. We could even do a little bit better here as far as performance goes. Instead of take, we can introduce an adapter called take exactly. So the difference between take and take exactly is entirely in the empty condition. The empty condition for take exactly simply checks that n equals 0. So you have to be very careful with this adapter and only use it on ranges that you know have at least n elements. But in this case, we do know that our range has at least n elements because we just counted them. We just ensure that we know that this is fine. And indeed, we can factor out this loop into a different algorithm called position, which is exactly the same as find if, except that it returns a number instead of a range or an iterator. And so finally, we've reached kind of the situation that we started with in C++, where we have an eager until algorithm. And if you look at the way we've ended up, these two implementations are very similar to each other, right? We're returning a new kind of range that starts from the element that we passed in and ends at this other algorithm call that tells us when to stop. So there's this nice mirroring between the two models that I really like. But it took us a lot more effort to get there in D. We had to be a lot more clever about things and take a lot more thought. Whereas in C++, this is kind of like an easy problem. Another example of this kind of phenomenon is let's look at splitting. So let's say instead of looking for a single element in our range, we're actually looking for like some contiguous sequence. And the algorithm for that in the C++ standard library is search. So search can search for an arbitrary subrange. And when we do that, we end up with 4 iterators, right? We get our initial, first, and last, and we also get mid.begin and mid.end, which is the result of our searching. And so again, the important aspect of the C++ model is that every pair of iterators denotes a unique range. So any 4 of these iterators we can combine any way we want to produce a new subrange. So let's say what I wanted was all 3 of these pieces as separate ranges. I can just put that together very easily using ranges subrange and return a tuple of all 3 pieces. Or maybe I only wanted these two pieces. And that's also easy. That's just like slightly changing which pairs of iterators I'm grouping together. And if I want these pieces instead, again, a very easy thing for me to put together. So we don't have these algorithms in the C++ standard library. We don't have a find split or a find split before. And it's questionable that we would even need them in the standard library because they're so easy to implement, right? You just call search and then you call subrange on the pieces you want. In fact, it's probably easier not to add them because then we would have to figure out what to name them exactly. And naming is always kind of like a hard problem. But indeed, this isn't the case. We don't have this property where it's easy to just group ranges together. And as a result, the D standard library actually does have these algorithms in it. And find split looks like this. Now, I don't expect anyone to be able to see this code. I just wanted to try to fit it on a slide. And this is D, the actual D implementation. This is not turned into C++. And so if you look at find split before, it is just as much code, very slightly different. And if you look at find split after, it is again just as much code, very slightly different. But the point I'm trying to illustrate is that like all these operations are actually hard to do in D, and there's a lot of cleverness that has to be involved in even getting them to work in the model at all. I did want to highlight one aspect of this implementation, which is this kind of happy case. So if I like simplify it a bit to remove the type inference part, what we have is something that looks actually very similar to the C++ implementation. This part right here is returning subrange from first to mid.end, and this part right here is subrange from mid.end to last. So for random access ranges, D has this very nice slicing syntax that lets you easily produce subranges like this. And so if the range that we're splitting and the range that we're splitting on are both random access, we have this like very easy implementation because we can use indices to get at the parts we want. And this very closely resembles the C++ implementation. However, if we don't have random access ranges, we can't do this indexing-based solution, and we have to write this very long thing that also uses take exactly in a few different places in order to get this to work. So there's a trade-off here. And so if I were to kind of plot C++ and D on maybe an efficiency frontier of complexity versus functionality, I think it's clear that the C++ model is more complex than the D model. I'm not sure anyone would necessarily disagree with me there. But it also provides more functionality. It's a lot easier to do a lot of things in C++, particularly with weaker iterator categories. There's a lot of things that you can do with bidirectional or even just forward iterators in C++ that are much harder to do in D. However, I kind of think that both models are good in the sense that they both offer a good trade-off of complexity versus functionality. Like there is no way to gain more functionality in D without introducing more complexity. And there's no way to make the C++ model less complex without also removing functionality. So I think they're both kind of in the right space for where they are. So now let's talk about Rust. And have you thought about just rewriting everything in Rust yet? The Rust iterator model, unlike the C++ and D models, is quite different. Here, so if we look at our same sequence again, we have an operation called next, and what next does is it gives us the next element. But when it gives us the next element, it's like gone. We can't get it again. So what I mean by gone isn't that it's destroyed from the original range. It's just that there's no way to get it back from the iterator. So unlike in D where we had the dereference operator, or in D where we had front, and we can just call it again to access the element again. In Rust, we can't do that. We just get next, and if we call next again, we get the next element, as the name might suggest. Rust also supports double-ended iterators with a next back function, which does the same thing, but from the end of the sequence instead of the beginning. So if we see how this operation maps onto a basis, like we only have one function. We just have next, but next serves all of these operations, as I'll get into. The basic Rust iterator structure looks like this. We just have our one function. This does everything. And its job is to advance to the next element in the range, read that element for us if it exists. And if it doesn't exist, indicate to us that we're done. And the way that Rust does it is that it returns an optional. And so a disengaged optional means that our sequence is now empty, and an engaged optional means that like this is actually the next value of the sequence. And this iterator is something that we're consuming as we go until next finally returns nothing. So as you can see, there's just one type, there's just one function. There's not really much lower you can get than one. This is pretty simple. It's also important to point out that this is not standard optional. It's very important for this model that we support optional references, and standard optional does not do that. So I'm not going to get into a huge rant about optional references, but it's just important to note that this is very important functionality that the standard library is currently missing. So if we look at trying to construct a Rust iterator out of a C++ iterator pair, if we have a forward iterator, we can do this fairly straightforwardly. The first thing we have to do is check to see if we're done or not. And then if we're not done, then we can read the next element, and we have to post increment at this point, right? We have to make sure that the first time we call next, we return the first element, and the next time we call next, we return the second element, and so on. And when first eventually does equal last, then we're done. We return a disengaged optional. We return our none. Now, if we had an input iterator, this wouldn't be valid because we would return the first element and then immediately increment the iterator. But the contract with an input iterator is that once you increment it, you've invalidated all the previous references to it. So for input iterator, we have to be a little bit more careful and ensure that we increment first before we dereference, rather than incrementing after we dereference. So we have this extra flag, but it's still very doable to construct a Rust iterator even out of a C++ input range. This is fine. It's not a problem. Our print all loop looks pretty different in that we have our while loop that calls next, which does all of our operations for us. It advances, it reads, or it fails. And then once we get that element, we just directly read it, dereference that optional to print it. So let's look at, again, our same examples of map and filter in the Rust model. And what we have to do there is we have to implement next. And so what next has to do is it has to pull the next element from the underlying iterator. If we have one, then we invoke our function onto it, producing a new element. And if we don't have one, then we just return no opt. And if you have a good implementation of optional, there's a shorthand for exactly this operation, which is if I have an element, give me a new element by invoking this function on it. And that operation is called map. And thanks to Sci, in C++ 23, we will have this on standard optional as well. And what I like about this is we have this really nice symmetry, is that we're implementing a map iterator in terms of map on an optional. Of course, in C++, this would be implementing transform in terms of transform on an optional, but we still have that same symmetry. So importantly, we're implementing our next in terms of the underlying next. We're just invoking this function on top. We just have the one type. We just have the two iterators, or we just have the two functions that we have to implement. So it's not a lot of code, as you can see. And there's not a lot of stuff we have to write outside of this extra function invocation as compared to C++ or even D. It's a lot more clear where the focus is. Implementing filter in Rust does not actually have the problems that we had in C++ or D, where we had to deal with where the first element was. And this is because next, just in terms of the model, all you do is look for the next element, and then you look for the next element, and you look for the next element after that. There's really no differentiation between the first element or the second element or the nth element. It's always just a simple loop. And so there isn't even any special handling or care that we have to do to make sure we get this right. We just have to worry about the fact that each next call does the right thing. And that is we loop, we pull the next element from the underlying iterator. We check to see if it satisfies our predicate. If it does, we return it. If we eventually run out of elements, we return a disengage optional. So as with map, we just have the one type and the two functions. Now, if this is something that you find interesting, you can find a complete implementation of like the Rust iterator model in this library that Tristan Brindle put together, tcbrindle/libflow, which is a pretty cool library. And now that we're in December and Advent of Code is in full swing, you can follow him on Twitter as well, because he tends to post solutions using his own library to all the problems. All right, so getting back to our table, so the Rust iter model, as I point out, we just have a single operation next, which is all three of these basis operations in one. However, it's not just Rust that has a model that looks like this. Python's iterator model is basically the same. It's a single function called next. The termination condition is a little bit different, whereas Rust returns an optional that is either engaged or not to indicate when the sequence is exhausted. Python throws an exception to indicate exhaustion. But otherwise, it's basically the same model. And Java's model is also very similar. It also has something called next, which reads and advances. And it also indicates done if it throws an exception. But it also has this extra function has next, which is an extra done check. So if you're going to draw a line anywhere in the middle of these languages, the line here seems to be a pretty good bet. Where everything above this line is what I've been calling the reading languages. So these are, again, our languages that have this distinct idempotent read operation, even though it's named differently. And the languages below this line are basically the iterator languages. Now, this may be confusing coming from C++, where we have something called iterator that does not actually resemble what Rust or Python or Java call iterators. But the thing is that all of those languages call what they do iterator. So I guess, majority wins in that sense. And not only do all those languages call what they have an iterator, but all these languages call their function next, which is pretty nice. So I guess it's nice to have consistency. However, not all the iterator languages are the same. There's another kind of interesting line to be drawn here, where Java is kind of like an odd outcast in this group. And let me kind of go through what I mean when I say that. So if we implement filter in Python, this looks very similar to what I showed for implementing filter in Rust, except it's even easier because since next throws an exception when it's done, we don't have this extra check that we have to do. We just have an infinite loop. When the underlying range runs out, that'll throw an exception, and that's all we need to do to satisfy our contract for filter. And since Java also has the same contract of throwing an exception on termination, it seems like we would be able to just do the same thing, produce the same loop, which is this nice infinite loop. Infinite loops are fast. But we also have to provide this extra has next. And the thing is, if we wrote next this way, we couldn't really provide has next because any kind of check that we would write, we would end up accidentally dropping the next element in the range, and we don't want to do that. So in order for has next to work at all, we need to cache an element. And so what has next has to do is it has to check to see if we have an element in that cache or if we can cache a new element. And so our actual filtering logic now moves into the set next function, which is implemented in terms of the underlying iterators has next and next operations. And once we have that, now we can implement next differently, where okay, well, if we don't have an element in our cache and we can't produce one, then we throw because we know we're exhausted. Otherwise, we need to grab our cached element and then empty the cache so we don't accidentally provide the same element multiple times and then return that. But if you look at this condition, this like, okay, if I don't have an element in the cache and I can't assign it, that's just not has next, right? And if we have like more operations on our optional, we can kind of reduce this take operation to a direct function. But if you look at what we have here, like if not has next, throw no such element. I mean, that is true for every iterator adapter that you would ever write in this model. That's what the contract is. That's what you're supposed to do. So it's a kind of weird thing to have to write. Not only is it just kind of a weird thing to have to write conceptually, but this is functionality that you can provide externally. So in Rust, we have this algorithm called peek. And so what peek does is it adapts an iterator to let you peek at the next element, because this is something that you can provide on top of any iterator. And so in Rust, this isn't something that you have to pay for, even if you don't use it. You can, if you need the functionality, you pay for it. And if you don't need the functionality, you don't. But Java doesn't give you that option. In Java, you pay for this expense for every iterator adapter. Every iterator adapter has to support it. So that's work that you have to do to implement them, and that's additional overhead when you're actually consuming it, which is less than great. So let's go back to our map filter example. So I showed earlier that for the reading languages, this will double invoke the operation in certain circumstances. So I have the same question here. How many times is some operation invoked for the iterator languages? And here we can definitively answer that it's definitely exactly 6. And so I'll go through and demonstrate why that might be the case. So if we look at what map and filter look like in Rust, when I'm getting the next element from the filter, of course, I have to call into maps next, and that's going to invoke the operation for me. But once I have this value, all I do again is access this value that I have. When I'm checking the predicate on the value and when I'm returning that value, I have this object directly. I never have to go back to the map again. So I know that it's never going to be invoked multiple times. The same is true for Python, which has the same kind of structure of the loop. Once I get my next element from the map, I just use that element. I don't have to go back to map. So I'm not invoking the function again. It's a lot more code in Java, but even though it's more dispersed, we still have the same structure. Once I get my next element, I'm only looking at this element that I have. I'm never going back to the map. So this is pretty nice. So you might ask yourself now, it's like, okay, well, we've avoided this kind of performance issue where we're double invoking we're double invoking the transformation. So does the Iterator model offer free performance? So let's look at a slightly different example, which is now I've replaced the filter with a drop at the end. So I'm still performing the same operation on every element, but I don't care about the first 2. I only care about the rest after that. And so I have the same question, which is how many times is some operation invoked in this context? And so here again, it's very easy to answer. That's definitely exactly 6. In our implementation of drop, we wouldn't forward the first 2 elements out. We would just skip them in a loop. But we still have to get them from the map, and getting them from the map still invokes the operation, even though we're throwing out the result. But in the reading languages, in C++ or D or C#, we would only have 4 invocations of the map. Because advancing and reading are distinct operations in those, for algorithms that only need to do advancing, of which there are quite a few, we don't pay the cost of reading. So that could make a pretty big difference. Now, in this particular example, this is an easy problem to avoid in Rust because I can just invert the order of the adapters that I'm applying. And if I do the drop before the map, then I'll only invoke the map 4 times. And this is because now the range that I'm mapping only has 4 elements. I'm still invoking the map on every element. I'm just changing the way that this works. Even though these 2 forms are semantically equivalent and they will produce the same elements going out, this kind of ordering tends to matter a lot more for the iterator languages than it does for the reading ones. Okay, so maybe we don't get free performance, but do we get equivalent functionality? And so to answer this question, I'll go back to findIf, the example that just keeps coming back in this talk. So in C++, again, so we can implement findIf. And one of the things we can do with this algorithm is that if I have a container, I can look for an element that's bad in the container. And if I find one, I can erase it using that iterator that I got back from findIf. And this works for vector, this works for dec, this works for map, this works for list, this even works for forward list. This just works. We get this nice cohesion between containers and iterators and algorithms. Things are just very easy to write. And this just naturally works for any user-defined container that supports erase as well. So let's see how to do this in Rust. And we start out and we immediately run into the problem of what does findIf even return for Rust? You might think, I was like, okay, well, we just copy what C++ does and we return an iterator. But we don't want to do that. Because what happens in this case is, well, if we return an iterator, well, we had to consume an element to see if it satisfies the predicate. So if we return the iterator at this point, well, now it's past that element. We can't get back to it because iterators in Rust can't move backwards. So that's not a very useful result. We can't really do anything with this after the fact. One thing we can return instead is the value that satisfies the predicate. And this is actually what findIf does in Rust. It returns an optional reference to the value that satisfies the predicate or nothing. You might recognize this from actually filter, which really does the same thing. So okay, so now I get my element. So I call findIf on my iterator, and I get maybe an element that's bad. But if I got one, okay, well, what do I do with it at this point? Like I have this reference. So if I had a vector and I knew it's contiguous, I could grab like the pointer to that element, subtract off data, and call it erase at index, which is just some function that instead of taking an iterator, takes a position to erase. So that'll work for vector, but it won't work for dec, of course. So I can generalize this a bit and bring back position, this algorithm that I showed earlier when talking about D, which now returns the index, an optional index of the first element that satisfies the predicate. And so now I have this more kind of general erase at index that can work for any container, but I really kind of hope that V is random access at this point. Now, this will work fine for vector, and this will work fine for dec, even though it's not contiguous. But while I can implement an erase at index for something like a linked list, that's going to be something pretty expensive because I did all this work walking through the list to find my element, and now I suddenly have to do all this work again, incrementing through the list just to be able to erase it. So that's also not great. We kind of lose this nice cohesion, and we can't really do the same sorts of things in the Rust model that we can do in the C++ one. So what about other algorithms? It's like, okay, well, maybe we don't need that kind of cohesion. So a copyable Rust iterator is isomorphic to a C++ forward range. This is fairly easy to demonstrate. And if it's non-copyable, it's isomorphic to a C++ 20 input range. In C++ 17, input iterators still had to be copyable. We weakened that restriction in C++ 20. So now even a Rust iterator that isn't copyable can be turned into an input range. And that works just fine. We can demonstrate that isomorphism. But what that means, of course, is that since we can't produce a range that's better than forward, we can't use an algorithm that requires more than forward. That's just because we can't meet those requirements. And so, for instance, we can't produce a generic sort. So Rust does provide a sort algorithm on slice, which is Rust's name for what C++ calls span. And so you can sort any random access contiguous thing you want as long as you can get a slice out of it. But you can't sort an arbitrary random access range. So in C++, if I had a vector of names and a vector of ages, I could zip them and sort the result. And this is something that works just fine. The outcome of this would be sorting both ranges at the same time. And we can do this because with random access iterators, we can sort any arbitrary random access range. But we can't do that in the Rust model. It doesn't have the ability to support this operation. And similarly, we can't do any of the other kinds of sorts. So there's no partial sort, there's no nth element, anything that might involve an operation like that. Similarly, none of the binary search algorithms work generically. You can't do it on an arbitrary iterator. So even though Rust lets you go backwards from the end, it doesn't let you go backwards arbitrarily. So algorithms like next permutation, pre-permutation, which require moving back and forth all the time, you can't do on a generic Rust iterator. You also can't do stable partition, and there's no that's a rotate in Rust. You just can't do it. You can do an unstable partition because that doesn't require bidirectional access, and so Rust does support that. But it returns an index, not an iterator, like a lot of these algorithms do. I suppose you could sort of write like a min element and a max element, but these are highly questionable algorithms, and they don't really make sense to provide since iterators consume elements as they go. These wouldn't be very useful. So overall, if I were to put Rust on this chart, it is obviously quite a bit less complex than the C++ or even the D models are. And it does offer less functionality than the other two. But I would argue it's on like this very nice sweet spot of functionality versus complexity. There's a lot that you can do with the Rust model it's still incredibly useful. Of course, Rust has language features that make it even more useful. But this talk is about like kind of what the library model is, and so I don't want to get into like traits here. One thing I will say though is that Java is clearly on the wrong side of this curve. The fact that it requires you to provide a has next, this adds complexity to every iterator adapter that you have to write. It adds overhead to every algorithm that you use, and there is no benefit that you get from this added complexity. There's no functionality gain. It's just strictly worse. So Java is on the wrong side of the curve for me. But Rust, I think, is pretty great. So at this point is where the C++ now talk came to an end, and this sort of ambivalent comparison between the three different languages, and saying that they're all good in their own different ways and they have their trade-offs. But there is another traversal model that I think is important to talk about. And when I originally presented the basis operations for consuming a sequence, I talked about, read, advance, and done, and I've shown examples where these aren't necessarily distinct functions. I've shown two models where we have three functions. I've shown two models where we have two different sets of two, and I've shown models that only have one. But this isn't really the complete story. And really, when I say that these are the basis operations, what I really meant was that these are the basis operations for external iteration. So what I mean by external operation is if we look at the C++ loop for print all, and if we look at the Rust loop for print all, these loops are different, right? They do slightly different things. That we're accessing elements differently. We're checking elements differently. But ultimately, what they have in common is that the loop is outside of the iterator. In both cases, we have this iterator thing, and we're pulling elements out of it, which is why this is sometimes called pull-based iteration. But either way, the loop is something that we do. When you write an algorithm, that algorithm is going to loop somehow itself. But there's an entirely different way that we can solve this problem, which is called internal iteration. Now, earlier, I was kind of shaming Java for its has next and this extra thing that it adds on top of the iterator model. But Java also has this other library called streams. So this picture on the top right is not actually the logo for streams. I don't know that streams actually has a logo. I just found a cool picture of a river that seems to fit the theme. And so the way that iterating over a stream works is that there is a function for each, and the loop is inside of that iterator. Like you don't have access to the loop. What the stream does is it pushes all of the elements out to you, and you have a function that you implement to just consume them. So this is why it's sometimes called push-based iteration. So instead of you manually pulling elements out of the iterator, or in this case, the stream, is pushing elements onto you. So if we write a stream from a C++ iterator pair, you can see that the loop for each, this is the same C++ iterator loop that we're all familiar with, but it's inside of this object and it's not exposed internally. Now, for each itself is kind of limited. Like, sure, it's useful to consume every element, but sometimes we might want to stop early. So it's more useful to provide a predicate-based approach that breaks the loop when the predicate finally returns false. Of course, at that point, it's not really for each. It's more like while. And for reasons, I'm moving the post increment later. And what the structure kind of allows is for the stream to be re-entrant. So you can consume some elements, and then you can call while again later and consume the subsequent elements. And this ensures that we do the right thing. Of course, it's also useful to return this information back to the user, whether you stopped early or not. So if while returns true, the stream has been exhausted, but if while returned false, there are still possibly some elements left to do. Now, this particular implementation, I wrote star first plus plus. This isn't an operation that's supported for all input iterators. So it's better to do pre-increment there, but to ensure that we do the pre-increment after the invocation. This ensures that we get all the elements kind of in the same way. And so much like in D, where we consumed the range, and in Rust, where we consume the iterator, the stream object itself is consumed. While is a non-const function, but this is intended to be a lightweight thing that then gets thrown out once it's consumed. Similarly, we can show what a stream looks like constructed from a Rust iterator, which again, the loop itself structurally is different, but we still have the while is inside of the implementation of the while for the Rust iterator. So if we go through, again, the map and filter examples, the structure here is now very different than what we saw from C++ D or Rust, where so we need to implement our maps while in terms of the underlying streams while. So the underlying stream is pushing us all of these elements. And what we have to do is make sure that we invoke our projection on every element before we pass them up to the user's predicate. And otherwise, there's no actual additional logic that we have to do. We just have to make sure that, like, as we're getting the steady flow of elements, that we're just modifying them correctly as they go out. We're invoking a projection. And what this lambda does is it's just function composition, right? We're invoking our projection before we're invoking the predicate that's passed in. And there's mapping with streams. Filter is likewise similar. I think actually the hardest part about implementing filter for streams is dealing with the fact that we actually have two different predicates. So we have our member predicate, which is the filter part of filter. And then we have this predicate that is passed in as the argument into while, which is just how streams work. And differentiating these two predicates, which both act on the same type, is a little bit of a challenge, because the two predicates act on different ways. Our filter predicate controls whether or not we pass the element up to the user's predicate, and the user's predicate controls whether or not we terminate early. So we just have to make sure that we can come up with names for these things and not confuse them. And so if you look at this implementation, and if you see that, so the underlying stream is going to pass us an element, and we're just directly accessing that element in our body. So you know, just based on the way that this is implemented, that we're not going to have this transform filter problem. You know for sure that every element is going to be transformed exactly one time, no matter what. And similarly, you know, kind of by construction, because we don't have these different operators for advance and done, that if we had a transform followed by a drop, that you know that transform will be applied to every element, even the ones that we don't need down the road. So in this sense, is very similar to the Rust model. So I've been working on an implementation of this that you can check out on GitHub. I called my library Rivers, similar because it's based on the Java streams library. And I named it Rivers largely because in C++20, the ranges views namespace is typically abbreviated RV. And so this is kind of cute that it's close to that. In addition to being inspired by the Java stream library, it's also inspired by Joaquin Lopez Munoz's Trans Rangers library, which you can check out at this link as well. The biggest difference between my library and his library is that in my library, as I'm showing on these slides, I'm passing the elements through all the way, whereas the way that he chose to approach it was to kind of reintroduce this notion of iterator, which are called cursors. So rather than passing forward elements, you get past something that dereferences into the element. So this has some advantages in terms of implementing algorithms like unique, but it also reintroduces the transform filter double transform issue, which I wanted to avoid, which is why he did it that way and I did it my way. So check out the library and tell me what you think about it. So now at this point, I think it's worth getting back and asking, well, why streams? Like, why do we even care about this? Why is this interesting? Like, why do we want to learn this like totally new approach to iteration? Like, is there some advantage to it? So let's talk about consuming a pipeline. Let's say I had something like I'm for each element of R that satisfies a particular predicate, I want to invoke this function. So in C++20, I can do R piped into filter on pred and pass that into for each on some function. So let's kind of peel back all of our abstraction layers and desugar all of this to see what this actually transforms into. So first we can peel off for each. And so what for each is going to do is it's going to grab first and last from the range, and it's going to iterate over it and invoke the function that you pass in. For each, probably the simplest algorithm in the standard library. It's going to be easier actually to present these loops as whiles instead of fors. So I'm just going to go ahead and rewrite that. But this is the same thing. So at this point, my iterators are filter iterators. So let's drop the filter abstraction as well. So what filter does for us is it kind of ensures that iterators always satisfy a predicate, and it does that by having these internal calls to find if. So we can de-sugar those as well. So now our iterators are iterators into R instead of the filter view. We just have these two additional calls to find if instead of simply incrementing. And let's also finally get rid of our first find if and just write that out as a while loop, and get rid of our second find if and also write that as a while loop. So here is our kind of whole implementation of that original ranges for each call, and what the model actually compiles down into. And so we get these two loops with this nested loop, and the second one, this is what things end up looking like. And so if you look at this check is actually very interesting. So if we had a predicate and our predicate returned false for every element, we just don't have a particular interesting range. The first loop would consume the whole range, and then there would be done. So we'd end up with first equal to last. And then we have to enter the second loop. So we have this extra check for first equals last again. So we don't need to do this extra check because we know that we're at the end, but it happens anyway. So that's overhead. We have this extra check that we have to do. And if you work through it further and see what happens, well, what happens when pred actually does accept some element when it does evaluate to true, you'll see that there's one extra check per element satisfying the predicate. And this overhead does add up over time. Like if you're filtering in a lot of elements, you end up with a lot of extra checks against end if what you're eventually doing is actually consuming the whole range. Now, this doesn't matter as much if you're not consuming the whole range, like if you're only taking a few elements or even just one. But if your intent is to consume the entire pipeline, this overhead adds up. So in my rivers library, you would write that code this way. So from is an algorithm that turns C++ range into a stream that then we can filter and then call for each on. It kind of looks like this. And so if we go through the same exercise of desugaring all of these algorithms, so for each is a simple invocation of while with a predicate that always returns true, as you might expect it to be. And we just went over what filter.while does. So what filter.while does is invokes the underlying while with a predicate that has an if check in it. So that desugars into this. So we have two return trues here. The first return true came from the function that we were passing into for each, because we're not stopping early, so we're always returning true. And the second return true is from the filter implementation to keep going on elements that don't satisfy the predicate. And these we can rewrite a bit because that's an easy optimization to make. Is just this unconditional return true. And at this point, we then desugar the from, which I've also shown earlier. It's like, how do we turn a range into a stream? And so what that while loop looks like is iterating over from first to last and invoking the predicate until it returns false. In this case, we have a lambda that always returns true. So this is very easy to optimize for the compiler. And this will basically turn into this loop. It'll desugar directly into that. And if you look at this, this is basically the same. This is actually exactly the same as the code that we would handwrite in order to do this operation. And so a lot of examples with streams in particular do directly compile down into the same or very close to the kind of code that we would write by hand, except we have to write like a lot less to get there. So it ends up being that like if you are consuming the entire pipeline, streams can be a lot more performant than ranges or even the Rust Iterator model. There's another example that is worth, I think, running through real quick, which is chain. So chain is an algorithm that we don't have in C++ 20, and we still won't have in C++ 23. But what it does is it concatenates multiple ranges together. So some languages call this concat. You might recognize it as just cat in Unix. And so what chain ABC does is it'll produce a range that gives us the elements 1, 2, 3, 4, 5, 6, 7, 8 as a direct sequence. And what chain also allows is to chain together ranges of different types as long as their underlying elements are compatible. So in this case, I have 2 vectors of int and 1 list of int. That's fine. They're both ranges of references to int. So this works without issue. So let's go over how to implement this in C++ real quick. This is one of the more complicated adapters to implement because we need a variant because our underlying iterator, we don't know which underlying iterator that we're currently on. So we need to be able to support all of them. That's a variant. And we have our basis operations. The done and the read operations are both fairly straightforward since variant equality already does the right thing for us. And reading is whichever iterator that we're currently holding onto, we just need to dereference that iterator. And so variant visitation solves that problem for us. But with advancing, std visit doesn't cut it. Because it's not enough to know which iterator we're advancing. It's very important to differentiate which vector of int iterator that we're advancing. Because we're not just going to increment the iterator that we're on. We also need to make sure that if we've hit the end of our current range, we need to move on to the next one. And that move on to the next one operation is very different from the first vector of int, in which case we move on to the list, and the last vector of int, in which case we're done. So we need to differentiate between all these cases properly. And in this case, I would resort to using a Boost MP11, which is a fantastic metaprogramming library that I would highly suggest that everyone use whenever they have metaprogramming issues. And MP11 has this algorithm called MP with index, which basically just takes a runtime index, which is in this case our variant index, and gives you a compile time constant that you can then use in other contexts where we need constant expressions. So in this case, I'm turning cur.index into a constant I, which I can use to increment the iterator that I'm on. And then I need to go through and also check to see if I'm done with this iterator. Now I know specifically which iterator I'm incrementing, so I can move on to the next one. And I also have to handle the case where maybe the next range is empty, so I have to keep going and incrementing until I run out of ranges. Now, it's not important that you necessarily understand the nuances of this implementation, but there are a few things I want to point out to this, which is that when we read, that's a branch. Like variant visitation, we need to branch on which thing we have in our variant to dereference it properly. When we're advancing, that's another branch because that's another variant visitation, and then another branch again to check to see if we're done. When we're checking to see if we're done, when we're doing our iterator comparison, that's another branch. And importantly, so I'm not talking about the branch that is the result of operator equals. I'm talking about the branch that is just to get the result of operator equals. So as you can see, there is 4 branches per element that we have to do in order to support this algorithm. So this is pretty bad. This is probably the worst case for the C++ iterator model, at least as far as I'm aware. But implementing chain in Rust is no walk in the park either, because we basically have the same problem of, we have to do this variant visitation kind of thing, except in this case, we have a tuple. And we have to be able to get the next element of whichever element in our tuple that we're on. And then we have to be able to handle the other case where we move forward to which. So if we factor out next one as the algorithm that gives us the next element of the tuple that we're on, we still have to handle the case where, okay, we don't have an element of this particular iterator. We've exhausted that one. We need to move on to the next one. So what we need to do is we need to increment our which index, and then we can just call next again. And of course, we need some kind of termination condition because eventually we will exhaust all of our elements, and so we can wrap this in a for loop or something like this. And so this is a branch because we need to know when we're done. And there's another branch here to make sure that we pull out the right element. So now this is also overhead. This is 2 branches per element instead of 4 branches per element, but it's still not super efficient. So let's run through how to do this with streams. So I'll start with for each and then go back to while in a bit once we've developed some intuition here. So in order to apply for each to all of our streams, we need a way to apply for each to a given stream, which is this generic lambda right here. And once I have this lambda, I can use std_apply to fold over invoking that lambda on every stream in my tuple. So this works. I don't super like using apply in this case. I would rather use tuple for each, which again is an algorithm that Boost MP11 provides. And once I have tuple for each, I don't really need the named lambda. I can just do that directly in line. And this actually reads great. In fact, it reads exactly like the definition of chain. Like, what does it mean to chain multiple streams together? It means that your for each for every stream calls for each on the underlying stream. This to me is beautiful. Not only does it read great and it is easy to implement, you will note that there are 0 branches in this code at all. So, of course, tuple for each has this conceptual notion of branching at compile time, but there's no branching that happens at runtime. We're just stamping out code for every stream in the tuple. So there's no overhead here at all. So of course, we don't have for each. The main algorithm that we want to implement is while, which isn't just sticking a return true at the end, because we do need to short circuit at some point. And in order to short circuit, we need a variable that we're keeping track of to see whether or not we need to keep going. And the way that we will update that is we'll provide a custom lambda into the underlying streams while, such that if the predicate that we pass in is going to return false, then we set keep going to false, and then we return false. So this both signals to that stream that we need to stop, and also signals to our outer while algorithm that we don't need to keep going anymore. And so if you look at this lambda, we can actually do this a lot simpler, because if not f of x return false else return true is very similar to just returning f of x. That is exactly the operation that we're doing. And since while actually tells us if we short circuit it or not, we can rewrite it this way, which is also like a pretty compact implementation. And so we do have a branch here, right? Because we know we need to short circuit at some point, but it's only a branch per stream. In the C++ implementation, we had 4 branches per element. In Rust, we had 2 branches per element. Here we only have 1 branch per stream, which is staggeringly fewer branches that we have to take. Additionally, this particular branch is very easily optimizable because this flag is either always going to be true for the entire duration of the algorithm, or at some point it's going to become false. And once it becomes false, it stays false. So as far as branching goes, it's about as easy to predict as they get. And we could even implement this a little bit differently, because there is already a logical operator that has this sort of short circuiting behavior to only keep going if all of the elements are true, and that operator is and. So in this case, we can implement chaining by simply calling a while on every stream with a fold expression, and this is what it looks like in the Rivers library as well. So ultimately, the comparison between internal and external iteration kind of boils down to what you want to do with them. So in the best case, if we are going to be consuming the entire pipeline or up to a certain point, internal iteration can generate code that's equivalent to handwritten loops or very close to it with very little overhead, which is pretty compelling. And depending on the choice of algorithms, they can be much faster than C++ or Rust in pathological cases. So in some benchmarks that I've tried to run, an example that does chain and a few other things can be 3, 4, or 5 times faster than the C++ model. Of course, this is the worst case. But streams are really built for consuming the whole pipeline. They're built for doing for each or min or count or any kind of generic fold that definitely either consumes the entire stream or stops at some point. And if you're not doing that, if you want to do something kind of more involved where you're actually manipulating elements, this is a very cumbersome approach as compared to the Rust or the C++ models. So as a result, and I spent a lot of time kind of trying to think about this problem and implementing this library and working through some issues. I'm still not entirely really sure where on this chart to place streams. It's even hard to answer the question of whether or not they're more or less complex than the Rust model. It's a very different way of thinking about how to implement some things. And so implementing chain in streams is a lot easier than implementing chain in Rust, but something like take is surprisingly complicated to do in streams, whereas it's very easy to do in Rust. So there's this weird kind of differentiation between them. It's also kind of difficult to compare functionality. So it's possible to prove isomorphism between the stream model and the Rust iterator model. So they can do the same sorts of things. So just like you can't sort a Rust iterator, you can't sort a stream. And so they support the same kind of algorithms, but streams are really built kind of differently. So you want to use them with different kinds of algorithms, and especially terminal operations are great for streams, but things that aren't terminal just aren't. So it's kind of difficult for me to know where to put this on the chart. So kind of putting it on top of Rust is at least seems like a good approximation for now. So that's kind of so that's the talk. Hopefully you got something out of it. If you were looking for a talk that kind of bashes the C++ model, I guess you kind of got that a little bit. And if you were hoping for a talk that talks about how great the C++ model is, well, you kind of got that too. If you were looking for something to tell you to rewrite everything in Rust, I'm happy to provide that for you. And so if you have any questions or if you want to follow up, you can find me on Twitter. You can find me on StackOverflow. You can check out this library on GitHub and tell me what you think. And so, let me know if you have any questions. All right, so there's a question. If you could travel in time, would you like C++ ranges to be different? So that's a super interesting question. So earlier I mentioned, and I put up this chart that shows that I think that C++ is kind of in the right complexity functionality space. And in a way, this isn't quite right. When we adopted C++20, there's a lot of things that we tried to change in the model in order for it to be backwards compatible. And originally, the design was to have a std2 namespace where an existing C++ range wasn't necessarily going to be a C++20 range. And examples of this are things like in C++17, in order to be a forward iterator, your reference has to be a true reference. So I showed an example earlier where I was sorting a zipped view. Zip does not give you true references. It gives you a tuple of references. So in the C++17 model, zip could not be random access. It had to be input. So as a result, to try to make these things work together so that in C++20 algorithms could use zip as random access, which is what you really want, because it certainly is random access. But you don't want to lie to the C++17 model and code that might rely on the fact that the reference is a true reference. There's this added stuff that we introduced where we have this notion not just of iterator category, but also of iterator concept. And this is pretty complicated. So we have these notions of like, well, zip is a C++17 input range, but it's a C++20 random access range, and that's kind of weird and complicated. We have other examples of adapters that aren't even C++17 ranges, but are C++20 ranges, which again is just like is weird and it's complicated. So definitely the lowest hanging fruit to answer this question is, I wish that we got this model right from the beginning. Like I wish we didn't have this restriction on the forward iterator reference type to begin with. Like I wish we added contiguous iterator from the beginning, which is again something that's new in C++20 and doesn't exist as a thing in C++17. And so, as far as if I'm strictly focusing on the model, that is something that adds a lot of complexity. But even assuming this, like, okay, so assuming we got everything right to begin with, I really do think that C++20, the model is a good model. It's useful. There's a lot of things that you can do in it that are important, and that functionality does come up. And the fact that you can't do these things in the Rust model is a glaring omission. If anything, I think the biggest thing, in writing a lot of ranges code that I want to be different in C++ isn't so much the ranges model as the language support around it. One of the things in particular, and I kind of briefly alluded to Rust traits and how easy it is to use traits and how easy it is to extend functionality on them. And even importantly, to write an algorithm where you take an iterator and you deduce the item type of that iterator in Rust is very easy to do. And it's much more cumbersome and convoluted in C++. It's more involved to write an iterator. It's more involved to write these things. And really, I think the biggest thing that C++ is missing is good language support about writing this kind of generic code. You can get there eventually. It just takes a lot of work, and it's not very nice as a result. So I think, as far as the model goes, the biggest thing would be to fix up the category concept notion and introduce contiguous from the get-go, and to never have had iterator traits to begin with. And in order to have been able to avoid having iterator traits, we would have needed some kind of proper customization mechanism, so that you could add all this stuff onto pointers, which of course don't have nested types or anything like that. So I hope that is kind of what you were looking for there.